All right, so I wanted to take a look at this question that I assigned to you. I wanted to give you a couple of hints. So for part A, it says derive an acceleration for the center of mass of the hoop as it rolls down the ramp. So let's do an extended free body diagram, and we'll see that we have a friction force that makes it want to spin. And we're going to have our typical mg pointing down from the center that applies no torque. And so we actually are going to be applying two ideas. One is the inclined plane idea. So we're going to have a normal force that goes this way, and we're going to have the normal, as we have the weight split into two components. One is the mg cos component, and the other is mg sine theta, like we always do. So when we write the expression for the acceleration, we actually have to worry about two things. We have to worry about the torque applied by the friction, so don't forget to write an equation for that. And it looks like we're having a moment of inertia there to help us. So the torque from the friction. And then we also have to write our standard formula from last semester, where we have the sum of the forces, this guy and this guy, produces mass times acceleration. So we actually have two equations to worry about to get the acceleration in the center of mass. Now it says derive an expression for the speed of the center of mass of the hoop at the bottom of the ramp. I would honestly use conservation of energy. I have this L here for the length, so I know the height is going to actually end up being L sine theta for my height. Kind of weird, but that's what they do. So I know I start off with an energy of mg L sine theta. And what happens to that energy? Well, it actually ends up becoming turned into kinetic energy, translational, and rotational kinetic energy both. And so we're going to solve for V using that expression. And remember, V is what we want to get. And we remember that V over R equals omega, so we use that substitution when we want to simplify this expression. Now, we want to replace the hoop with a disk having a mass m and a radius r. So the hoop's mass is all distributed on the edge here. So every single part of that hoop's mass has to turn in a really, really, really big circle. Now if we have a solid disk, some of that mass is closer to the center. So think about what that means in terms of how hard that's going to be to spin, and think about the speed that it's going to get here for the disk versus here for the hoop. And think about what that will imply for it reaching the bottom of the edge of the table. And actually that was part D. I skipped part C, sorry about that. If you need a little bit more of a hint for D, I'll just tell you that I of a disk is 1/2 mr squared. That's the one that I had memorized. It might not be a bad one to memorize, but you honestly don't need to. You can make a qualitative argument here. Now for part C, you've got this horizontal speed, right? So you're going to actually use some projectile motion stuff to go ahead and solve. So that's just a quick set of little hints for this problem. On the Google Doc next to this, I'm going to actually have you submit your answers as best as you can in the form of some multiple choice selection. So go ahead and do that. And if you notice on this form I ask your SHCP email, that's so I can actually email you an answer key so you know what you got right and what you got wrong.